Ladies and gentlemen, welcome to our today's keynote. Thank you for coming in time. Those who are leaving later, they will not thank. Yes. I'm happy also to introduce you to Susan Howard, who is the Peter Chen sponsor, yes, and from the representative of the sponsor from the Elsevier editors. So thank you very much for that. And yesterday evening we had a wonderful dinner, and the honor of Il-Yeol is now on you, Peter Chen. Thank you very much.
Congratulations.
Thank you.
Good job. I'm very happy to have the honor to chair this keynote of Il-Yeol. But I'm also sorry that this keynote will be only short, because presenting Il-Yeol takes a lot of time. If you are reading his curriculum detail, then it's 56 pages document in the internet with a 53 pages list of publications. So it's incredible what Il-Yeol did in the past. And now I lost my... Sorry. Yeah, Il-Yeol is professor at the Drexel University in Philadelphia, and in parallel he is an affiliated professor of KIST, which is the former Korean Advanced Institute of Science and Technology, and it's now a modern research university with several places in Korea. He's made his PhD, his Bachelor of Sciences at the Korean University in Seoul, then went to the United States and made his master, if I'm right, at the Louisiana State University at that time already in computer science. His bachelor was in nuclear engineering, as I learned from his curriculum vitae. His PhD also he made in Louisiana State University, and then he changed after some time there as a research assistant to Drexel University, where he has been an assistant associate and since 2008 a full professor in parallel to his affiliation to the KIST. His research interests are quite broad, and I'll tell you some of them. Really, the most important one is conceptual modeling, and a lot of papers of Il-Yeol about conceptual modeling. He's also interested in design and performance optimization of data warehouses. He's researching big data and online analytic processing. He has worked on object-oriented analysis and design techniques, and finally, also he is engaged in the analysis of medical and healthcare data. His list, as I said before, of honors and awards is quite a long one. He has honors in teaching, honors in research, honors best papers, awards, etc. And now, since yesterday, Il-Yeol Song is our new leader, Chen Hourly. I'm very happy now that it's maybe shorter. I'm very happy now to listen to your presentations and to see their Il-Yeol supporters.
Thank you, Andy. I wish my wife was here. She would be very happy to listen to this introduction. Right, today I'd like to talk about big data technologies and project management. Maybe I should say more on conceptual modeling on my own research areas and topics, but I thought maybe you are more interested in this topic rather than older topic, because the older topic already has gone, and these are new topics. I think you are looking for more newer topics here. So that's my university photo. My university logo is dragon. I was born in the era of dragon in Asian 12 animal systems. So when I went there for job interview, I saw Drexel's logo is dragon. So I knew It is my university. And then I have been there for 28 years now.
No.
So anyway, for last several years, I have been involved with several big data projects, and then I served as the deputy director of NSF IUCRC Research Center on Visual and Decision Informatics, and also I have been involved with creating about $100 million project. So I learned a lot. So I'd like to share with you my what I learned and what I experienced and what I thought today. So you saw, if you look at the internet, you see a lot of big data technology terminology, which are well beyond our understanding here. And then also you can see there is so-called big data infrastructure. There are many terminology like in-memory, enterprise data warehouse, local data warehouse, and the visualization, the HBase, zookeeper, data access, Hadoop, NoSQL, data governance, data virtualization, predictive, prescriptive, etc., etc. So we are overwhelmed with all those. So about 3 years ago, when I became the director of the research center, I was overwhelmed, and then I thought what I should do. So I should begin to learn about them. Also recently, you saw a lot of different database systems. So from beginning from relational databases, and then we have MySQL, and then we begin to see from 2006 big table from Google, and then Amazon. These days, NoSQL, everybody is talking about NoSQL. We have NewSQL, we have in-memory computing, in-memory grid computing, cloud computing, hybrid cloud. So how we cope with all these technologies here? Also, some of you may know this is so-called a Gartner hype cycle on emerging technologies. So if you can see here, big data is in, how to see here, right here. So this is the area you begin to see people became a little bit disappointed by unsuccessful rate of project management. So there are a lot of technology, emerging technologies going on here. So in 2015, they removed big data from this hype cycle. So wow. So Gartner dropped the big data off the hype cycle this year. Wow. So the Gartner analyst, Bessie Burton, says that big data is no more emerging technology. It is just our common technology these days. We have to live with it. So it is here. We are indeed living in the era of big data technologies. We cannot deny that. Right? So we are overwhelmed or overloaded technology terminologies. So we need to understand a little bit. So what the big data market is over right now $30 billion, and then in a few years later it will become $50 billion. So there are a lot of monies, a lot of people's interests are going on here. So my work, as I said, I served as the deputy director of NSF IUCRC project on visual and decision informatics. So I worked with 13 different companies, including IBM, Lockheed Martin, Johnson & Johnson, Children's Hospital of Philadelphia, etc. So when I talk with the director of the research team and R&D team, at first I had to shut my mouth because I didn't understand what they are talking about. So I had to begin to work with them to learn what they want and then what we can do for them. So from 1 year ago, I have been involved with creating a really large smart healthcare project. So they are how we take advantage of these big data technologies. So based on my experience, I studied, I learned, I discussed with them, and then here I made a quick summary. So today I will cover, I will not cover like a big data growth, size, everybody knows that. History of big data, I will not talk about it. But I want to talk about so-called the 5 V's of big data a little bit, and I'll give you a very quick summary review of a big data technology at 10,000 feet high, and then I'll think a little bit about conceptual modeling and big data, how they are related. And then when I thought about what we can do as a conceptual modeler, I think maybe NoSQL is the area we can do most at this time. So I spent a little bit detailed time on NoSQL, especially some what are the modeling aspects in NoSQL in general, and then some of my experiments with the column stores and graph databases, and they kept here. And then I made a summary on the project management idea. So what we should do in managing big data projects, and what are some research topics available to us, not to everyone, to us, and then some of my own research projects, and then I made a conclusion to it. So what I'm talking is really just the surface of the big iceberg here. So you can see that there are a lot more technical detail you may want to investigate after this talk. So someday we want to break the wall to create some innovative ideas out of this talk here. So why big data? So most of you know that we have a lot of new technology, computing technology, and then suddenly we have a lot of data from all the sensors, logic, webs, etc. And then we create the so-called data-driven paradigm because data suddenly became very, very important and then available to us. Instead of just extracting part of it, now we have a whole data. And then we are, in order to cope with them, we have a big data technology. So you can see that storage technology was rapidly increasing, and the price exponentially came down, and the CPU cost is also exponentially came down. Network bandwidth came up exponentially, and then today we have a lot of fast stream data processing, real-time data processing, etc. I'd like to introduce one wonderful book called the Big Data Revolutions. So when I read this book about 2.5 years ago, it opened my eyes on what the big data is all about. It really gives a lot of examples and then a lot of our philosophical thinking on how we can think about big data. So some of the ideas like use of whole data rather than sampling, accept the probability rather than just say 100%. And then big data outperform experts like Amazon example. People's comments are more acceptable, more accurate than experts' opinion. And then we need to accept the correlation. There are some correlation, but we don't know why that happened. Not all the time, technology gives us 100% correct solutions. And the datafication. So we can create the data from any sources which we couldn't think in advance or in the past. So there are many ways of generating data which we didn't know. So we need to learn how to quantify, how to measure, and then let the data speak itself. And then how we take advantage of all the data to make business opportunities. So that is a value here. Right? So all the trends give Gartner to create the so-called 5 types of data we have not seen in the past. I mean, all the data in big data area can be classified into those 5, like operational data. These are data what we have been dealing with in OLTP systems. And then we have dark data. Some data we didn't pay attention a lot, like email, reports, etc. So we call this semi-structured or unstructured data. And then we have commercial data. There are many data industry are generating. So have we taken advantage of all those data? Okay. Now we have suddenly social media data for trend analysis. We need to trend analysis in real time to generate the coupon to deliver on the right place to the right people. And then a lot of social data from social media, and then public data from government on the web. So how we take advantage of those public data as well. So the big data are dealing with all those 5 types of data. So what is the big data? All of you know what is the 3D. So I won't spend too much time on this, but I do want to show my slide because I spent a lot of time to create the slides. So everybody knows 3D is a volume velocity variety. They were created by one of the Gartner's current vice president in early 2000. So at the first time it was not very popular, but late 2010 area, suddenly it became got a lot of attention. So what is the big data? So 3D is a volume velocity velocity. So volume is we have due to the datafication and then sources, suddenly we got a lot of data. Data are coming from your OLTP, OLAP, dark data, etc. And then we have technology to deal with that. So our scale of data is petabyte, exabyte level. But that's technology solution. So if you pay money, you can deal with volume. And the velocity, which is data are fastly generated, and then we need to extract data for the data. So we are dealing with the processing mode, not just the batch mode or interactive mode, but near real time or even real time. So that's the same technology solution. So even if you write a program, sometimes we can do it, but the accuracy and qualities are not always guaranteed. And the third one, variety is what I really interesting. And the conceptual modeling people, this is the area we are concerned most. But unfortunately, that's a software solution. It's a labor intensive, human intensive. So still, solution is not perfect enough. And then next to 4B is veracity. So how we trust our data? Our data is complete, consistent. Everybody agrees, reliable, trustable, right? So whatever you see from screen may not be always correct. So that's sort of the eventual consistency concept from NoSQL world. But most of all, business people, when I talk with the business people, they don't care what's the 3B, 4B, etc. They all come down to the last word called so what? What's it to me? Right? What can I do? What those technology data can do for my business? So some people prefer to define big data into 3B, 4B, but when you talk with the business people, 5B is absolutely more preferable. So they are looking for actionable knowledge and return on investment. So without that, they spend like several $1 million on technology, Hadoop, distributed file system, NoSQL system, hire the programmer, etc. But if they cannot produce any value, you are not very successful here. So I'd like to use this 5B in my presentation today. So volume and velocity are challenging. Everybody agrees that. Processing real-time data is still difficult issue. Right? However, variety and velocity are far more challenging. So from research point of view, I think that you should focus on dealing with the variety and velocity in our conceptual modeling community. However, value is the most challenging. Even if you model a lot of different types of data, and then you analyze the accuracy, consistency, incompleteness, etc., but if you cannot bring value to your business, your project is not successful. So everything eventually going up to the value. So value gives us the opportunity for innovative solution, for research and the business. And then impact on technology, society, business, and your promotion, your tenure cases. So, then what's wrong with the relational database? We have been happy with the relational database for almost like over 30 years. And then our database professor, we were happy because we just wanted to teach the SQL. So, and then normalization, ER modeling. So Shamna Watt's book does not have to be updated every other year like these days. Right? So, what's wrong with our relational databases? RDBMS cannot be handled very well for the 3 weeks. It cannot scale up and scale relational databases that inherently have a problem in scalability because of its architecture. Even if you have a multi-node computer, multi-CPU, internal communication is very expensive and very difficult to scale up. And then difficult to deal with faster data because of you need to break out the data into multiple tables. Join becomes expensive, so analytics has a problem, has many problems. And then RBMS is also using a so-called schema override. So sometimes we want to quickly process data without relying on schema here. So that's why NoSQL technology were invented. And the ACID also properties are sometimes too rigid. I want to quickly update my data and then let everybody see. And then it doesn't matter when I see you updated your Facebook just 3 seconds ago. It doesn't matter when I see your 3 seconds ago update right now. I can see every 5 minutes, 2 minutes, even 5 seconds. So eventual consistency sometimes does not matter much. RDBMS cluster are so-called Spark, single point of failure. In other words, in a relational database cluster, if one node is broken, your system may go to broke. So that's a big problem in the relational database. So upgrading hardware is very expensive. Oracle makes a lot of money by selling software to the cluster machines. Also, RDBMS has a so-called impedance mismatch, which I discuss a little bit more later. This means that real-world data like report or forms contain the data that are coming from the different tables. Human is consuming the data together as a set, but your relational database break the data into pieces, into atomic tables. So this has been accepted for many years when our data size was small and the join was good enough to process it. But now, sometimes it's not acceptable. So hence, so we need a new architecture with transaction management, so we created. So I did a very quick review of the big data technology that I put selected here instead of a very detailed level. So Hadoop 1 and 2. Everybody talks about Hadoop, not anymore these days, but just until 2 years ago, everybody talked about Hadoop 1 and 2. So Hadoop is a open source version of a very reduced parallel processing paradigm. And then the two major features of Hadoop is the scalability and the fault tolerance. So I can show you a little bit later why Hadoop architecture has this scalability and fault tolerance. And the Hadoop 1 mainly works on batch-oriented system for single machine. So a few years ago, people produced a so-called Hadoop 2, which has a more diverse platform and which has a more wider level of ecosystems learning. So they split the Hadoop, distributed the file system framework into two components, HDFS and YARN. So this architecture shows that Hadoop has a wonderful facility of scalability. So this is the master node and then this is your slave nodes. So if you need more storage or computing power, you can just add more computer there. So these are commodity PCs. So this architecture is handling scalability in that manner. And the fault tolerance means the replication. The data is replicated into multiple machines. So in this way, even though one is broken, and then the master node automatically figure out or to the next level. So this is the fault tolerance features. So this Hadoop, this architecture created three important ideas in cluster environment. Number one, we can handle scalability in software. Number two, we can handle fault tolerant features in software manner. And then we can handle load balancing. For example, not every computer will have the same main memory, the same hard disk space. And then your master node can manage all those automatically by load balancing so that you don't have a hard stop. So most of the database technologies are also using this technology for scalability and the fault tolerance and the load balancing. So the reason people like the Hadoop a lot is it has a lot of good ecosystems, from storage to the storage management, the query processing, databases, machine learning, even machine learning rapid algorithms. A lot of algorithms were able to run on top of Hadoop systems. So even Hadoop 2, they have a more refined, more online interactive systems now. So in Hadoop 1, only batch systems were available. So all the data and little data were written in the disk. And the Hadoop 2, it became a little bit quicker, and then it can handle different types of processing mode. But these days, Spark is the most widely talked about technology. So I visited Korea during last September, a month ago, and we were writing parallel processing architecture paper. And then we sent our initial draft to one of the well-known people at IBM in Germany, and they said that your paper will not be accepted until you compare your performance to Spark environment. So everybody is now talking about the Spark here. And the most hot technology here. So why Spark is a much better solution than Hadoop? Spark does not replace Hadoop, but it can do almost 90% of what Hadoop environment can do. While Hadoop is a disk-based system, Spark is a memory-based system. So a lot of computations are done in memory. And then, so when you have a machine learning algorithm running in like a PageRank or machine learning algorithm in Spark, it runs 100 times faster. So in this group for iterative or real-time processing. So real-time video processing, real-time advertising processing in Yahoo is done by Spark right now. So the guy who invented this technology was a PhD student at Berkeley, and he received a 2014 ACM Best Dissertation Award. Now he's an MIT professor. So another important feature of Spark is a so-called RDD, Resilient Distributed Data Set. This is a set of data set that is used in iterative algorithm. The beauty of this algorithm is that you don't need a backup. It stores all the lineage by algorithmic way. So even if there are some fault tolerant or you want to go back to previous iteration, it can just automatically go back. So computation becomes very efficient. So it has a fault tolerant distributed memory abstraction that avoids replication. So in-memory feature, RDD, these are two main features of Spark that make it popular. So suddenly we have a NoSQL databases. So I will talk about 30 minutes about NoSQL database later. So right now, just a quick landscape on NoSQL. So we have 4 types: key value, column store, document database, graph database. So basically, graph database is not really NoSQL in the sense that it has a completely different architecture and a different purpose from the first 3. So we'll talk about that later. And then also you might heard the term called the USQL. So not only NoSQL, but also we have USQL. So USQL was invented by the people who said that if NoSQL is good, but it has a disadvantage, then why do we combine advantages of a relational database and NoSQL together? So they created a new system called the USQL. So USQL is a relational database supporting ACID properties and SQL. And then, but on the other hand, it supports a cluster environment. So you can use a commodity PC, just like the Hadoop architecture I just showed you, instead of a very expensive single server architecture. So it supports a scalability and performance here. So you can handle OLTP workload, and some of you NoSQL systems can do both OLTP and OLAP. So they call hybrid transaction management systems. So they support SD and SQL, but in terms of data type, they have limited support on variety because it's purely relational database systems. So Google Spanner, WatchDB by Microsoft Breaker, MemSQL, UDB clusters, they are planned to be NoSQL. And some of them are based on in-memory computing technologies. So brief comparison here. So NoSQL is a relational SQL, support SD, support the horizontal scalability, but it's not schemaless. It is schema. So in-memory computing is also very popular these days. So if you have some money to improve your technology, people love to invest into in-memory computing technology. So in-memory computing means initially your data in hard disk, but for all the computation, during the transition time, every data is in memory. So you need a little bigger memory than conventional database systems. So what if your data does not fit into main memory? Then you still use several different technology to support it. So this simplifies a lot of physical architecture. You don't need to rely on a lot of indexing, recovery, backup, that kind of procedure. So in-memory computing is very popular these days in using NoSQL, USQL, data warehousing, analytics, etc. So they are ACID compliant relational database OpenSQL, and the durability are supported by snapshot technology and the transaction load. So in-memory in large, we have 2 types of in-memory system. One is just an in-memory database. The other one is an in-memory data grid. So the difference between them is in-memory database is run on single server cluster. But in-memory data grid runs on just like the NoSQL-like architecture. you are using a lot of commodity PC, connecting, supporting scalability, etc. So they use a key value store technology to store the data in everywhere for the load balancing. So this is very popular technology these days. So everybody knows what is clustering. So we have three architectures of clustering. Infrastructure as a service, where the companies the vendors are managing hardware environment, but your application programmer managing your software environment. And the platform as a service is only application data are managed by client. In the software as a service, you put everything into, including your own data, your own software, whatever. You are using a vendor's software instead of your own software. So one of the key recent new development in cloud computing is so-called the hybrid cloud computing. So this means that we need to decide what to keep in our premise cloud, in our own business databases, and what to put in our public cloud. So you need to think about what to put, how to integrate them. So here, data integration and security became two critical issues. The communication network is so data integration is done at the cloud level. So your cloud is keeping track of all the data from your mobile phone, social networks, but your key business data are still in the private, your cloud view. So when you analyze the data based on both the transaction data and then mobile social service from internet, now you need a so-called hybrid cloud technology for data integration. So these are both variable, dynamic, and highly changeable workload. In the warehousing area, we also traditionally use the so-called ETL technology. So which means that traditionally you receive the data and then perform ETL first and then store it to data warehouse. But Hadoop came out, and then we need to quickly process the real-time data. Then this ETL became too slow. So people invented the ELT technique, mainly preceded by Oracle here. So ETL is performed after you load it here, after you load the data warehouse, and then you perform the ETL, some extraction and the loading technologies. And then you use some virtualization technology. So data virtualization is also very popular these days in industry level. So data virtualization means it can be done in any level of your pipeline here. So you can have a virtual ODS, or you can have a virtual data mart here. So virtual software means you don't physically create the data. You are materializing data in an integrated way by combining data from multiple sources. So I tried to investigate what are the technologies behind the data, but there were not many sources available. But I'm sure it is using schema integration, data integration technology. So I'd like to give that the homework to Carlo and the Martini. Carlo and the Shama. So they are your homework on what are the theory behind this data virtualization. So I'll get your report next week. Right, so then data warehousing technologies, getting ELT and data virtualization, Hadoop, Spark, etc. Now we have so-called modern logical data warehouses. So that means your data warehousing architecture is now accommodating Hadoop technology and NoSQL technology. So some data are stored in pre-Hadoop, so-called data lake. Data lake is a storage space that just keep the raw data as it is without process. So we need another software layer to extract the data and load it into virtualization or data warehousing. So we need to big data warehousing technology live happily with a big data cluster with a original structured relational data warehouses and the clusters and the real-time store with a SQL. So your online analytic processing, business intelligence, data warehousing, all the application can get the data from these three areas. So this is quite stable technology these days. So these are some areas that I have been involved in. So let me make a quick summary in just one slide here. So big data technologies are very, very complex. We need to evolve, and they will evolve. They are rapid. I think vendors are merging each other. They are buying new technology very, very quickly. So big data technologies address issues on web, mobile, social, cloud, and the big data analytics. So these are key pointers of the technology here. And the Hadoop ecosystem will also evolve. There are a lot of hypes. Just up till last year, the Hadoop market is still very low. Out of a $38 billion market, Hadoop market is still less than 1% because of the programming difficulty. And then, but Spark will certainly came out and will dominate the real-time and the parallel processing market. So if you want to, if any of your students wants to make their resume look good, their high paycheck, they need to talk about this Spark. And the NoSQL systems they stand out query language and the sub-discipline, which I will cover here later. Here, discipline means that even if so many people say that NoSQL does not need a design, but actually I found that we need a design. And then the model could be still useful. I will show you some examples. Not as much as relational databases, but we still need those technologies. And then also we need to set up query language. We have been fell in love with SQL for so many years. We cannot get away with that. And then in-memory computing is widely used in NoSQL, NewSQL, analytics area. So in the analytics area, in-memory computing is the best technology to use. And the Hadoop and the EDW, Enterprise Data Warehouse, will coexist for many years to come. So your data warehouse will not go away. They will stay with many years to come with the Hadoop and then even Spark. And in the industry and the research area, the big driving force behind the big data technology is IoT. I think there are, even these days, there are many conferences on just focusing on IoT and the smart city. So let me move to the conceptual modeling and the big data. So what can you do? According to conceptual modeling.org created by our community here, it says that it is about describing the semantics of software applications. And also it says that we can describe the structural model in terms of whatever we want. Some model is using entity relationship attribute, some model using class attribute, aggregate. And also we model behavior and the functional models. And also we model interactions with user interfaces. So actually, you can see that we do a lot of things. We are not just modeling structure of our database here. Also, we can enable client and analysts to understand one another. We can communicate with the people. And then analysts to communicate with industry people. Successful. So this is people may have a different definition of a conceptual modeling, but this is what we agree that we put on our ER conceptual modeling.org. So is conceptual modeling bad for big data? Many people said that we don't need to design anymore. So is it bad? It's not bad. So all models are wrong, but some are useful. That's why we have been practicing. So you don't always create the best model from scratch at the beginning, first start. With the multiple iteration, we have to try out it. So I think why we can do something for big data here. First of all, I think we are the good thinkers. You agree? Whether you agree with me or not, we are good thinkers because we know how to think in terms of components, and we know how to put them together, and we know how to check the quality of our schema, and we know how it works, how user like it or not. We can evaluate. We are good thinkers. So trust yourself. And also, we found that conceptual modeling is a very useful in abstracting complex concepts, in the understanding, managing, architecting, and the teaching big data technology. I know that many of my colleagues are excellent teachers. And so conceptual modeling is very good in handling a variety of big data, as we said earlier. So that's obvious. So we can play some role in data integration, big data warehousing, cloud, metadata, data creation. Data creation is not very widely recognized by computer science people, but in information science people where I belong to, it's a big deal. How we save all these data for 10 years, 20 years, 100 years later. What to keep, how to keep, can you read, at that time, we have technologies that can read the data we saved right now. It will be able to compare it. So, what data to keep, etc., is a big deal in that area, and then we can play some role there. So, conceptual modeling is used for managing big data projects, and then we can identify big data requirements and then connect the business goals and technology and the business people want. And then we can identify big data use cases and build the architecture, and the select a platform. Many people are confused which NoSQL system to use, which NoSQL system to use, or even relational NoSQL, or memory computing, what memory size, what disk spaces, what hybrid cloud infrastructure technology to use. How we can help them to choose the right platform. And then also we can become a leader in big data projects. So when I say that I'm the director of an example research center, business people trust me that I'm an expert in big data, expert in everything. Just like if you have a PhD degree in electrical engineering, everybody wants to know how to fix TV, computer, etc. So, but in fact, you know that we are not. So we have to deal with a lot of things that we can live along. So there are new trends in USA, so-called the CDO, Chief Data Officer. That's a brand new kind of, from 3 years ago, it became very popular in major industry. So we can become a CDO also. So I'll tell you a little bit more later on what involved in CDO. And then perform high-level analysis. We can become a citizen data analyst. Citizen data analyst means that you don't have to write the machine learning algorithm, program R for statistical analysis. These days, there are a lot of powerful tools. You can use the tools to analyze high level. Your student or your subordinate will do R programming, Java programming, C++ programming. But you need to create the conceptual structure, and then you can do very high level aggregated data analysis. Because citizen data scientists. And then we can evaluate the big data project. Is that really worthwhile to invest the money? Is it really worthwhile to hire new people here? So also we can help manage a variety of big data in organization. In some organizations, they don't know what kind of data they have, what kind of data they can create. So you can apply so-called datafication, where you can create more data, you can give some ideas on how to use that. So all these end up with the deriving the value here. That's why I don't want to use V in my definition of big data. So there are many other things like domain analysis. Our community is excellent in domain analysis. Like for example, in smart city, how we do domain analysis. I'll show you later one slide on our domain analysis on a smart city later today. And then data governance and master data management. Without this, your project are doomed to fail. So, an approximate answer to the right problem is better than just the exact answer to approximate the problem. So we need to find out, define the problem. That's what we can do very well. We are good at identifying requirements and then analyzing, evaluating. So 5% conceptual model here. So in volume area, they are physical, but you can still help other people on how to organize, how to identify, how to extract important data and the metadata. In the velocity area, you can work on how to extract what data, how frequently, extract important data and metadata. And the variety area, obviously you can model variety in terms of hierarchy, complex message structure, networks, and then talk about integration and the dealing with the big data warehouses. In the velocity area, a lot of you wrote a paper on checking quality of requirements, quality of the schema, and how to check a consistency and completeness in your ER diagram or requirement or your software code. So you can transport both your theory and research practice to project big data area. And then finally, value is maybe more relevant to business people. But we, these days, a single person cannot do everything. We have to work together. So we can manage together with the business people or low-level programming people together in how to extract business value out of this big data project. So now let me move to NoSQL here. So NoSQL does not mean it is not SQL. Roughly NoSQL means not only SQL. It is a buzzword used in 2009 San Francisco Bureau. So the organizer was looking for a nice hashtag name. So he couldn't find the good name at that time. So somebody suggested NoSQL, and the user said a real good name, tag name. Just meaning that non-relational, distributed, scalable, and then non-relational in the sense that can model variety. And then the scalability in the sense that it supports the cluster and the distributed. So any database system having that kind of system come, and then they become NoSQL. So don't worry about too much about definition of NoSQL here. We don't have a precise definition. So roughly, it means open source or identity scaling, and then scalability, fault tolerant, non-relational, schema list. They are major characteristics of this NoSQL. So NoSQL was designed with the needs of big data, needs of handling those 5 types of data rather than just relational data, and then cloud in mind with a lot of users. So there are 2 most important features: scalability and performance, nothing else. They don't care too much about consistency, performance and scalability. Like online advertisement. So, for example, when I opened one Korean website at Prague last week, the Prague advertisement came up. When I opened the same website here in Stockholm at my hotel, the Swedish advertisement came up. So, we need to customize the advertisement, everything. So one of the most important features of NoSQL is supporting non-relational data type and the schema list. That means we can create the attribute dynamically. And then not every row needs to have the same types of attributes. And then scale out massively. Instead of scale up, we want to add more commodity pieces for scalability. And the low cost. Of course, it costs some money, but low cost is comparative. Low cost and relational. And the support scalability, performance tolerance. But this feature, as I showed you earlier, it comes from the architecture of a Hadoop distributed file system-based architecture. But it may or may not guarantee full SD properties. And then real-time, non-uniform big data. So according to survey, scalability and the schema flexibility are 2 major reasons people are using NoSQL systems. So NoSQL is a making shift from relational to NoSQL, and then the relational database is scale up. So you buy more powerful, you add more CPU, you add more disk in a single system, and you create a more powerful bandwidth. But in NoSQL system, you add more PC types. So instead of purchasing a very expensive server, you add more low-level, cheaper, low-cost commodity pieces. So the main difference is from our modeling point of view. I didn't care about other programming aspects too much. So from our conceptual modeling community point of view, these are 4 major issues we need to deal with when we deal with NoSQL. Schema list, impedance mismatch, low join, and then how to handle redundancy. So these facilitate the ease of application development. If you look at the internet, many NoSQL programmers say that I was able to develop working code quickly than in other cases, other relational cases. Because I don't have to do a lot of Java mapping between your in-memory structure to disk structures. They can have a roughly like a one-to-one mapping between in-memory structure and the disk structure. So for example, this is an example of a dynamic column generation in an HBase like a system. So suppose I have an employee with a employee data with a column family, which is a massive table name, and the attribute of the name, gender, city, and I want to add a to President Obama and Hillary. I think one of my slides is disappeared. Oh my God, although it's finished. I need to show this one first. So why we call the NoSQL is dynamic and the schema-free? So suppose I want to create these two former presidents of US here. Then first you create a table just with a table name only. You create the table command. The create command has only table name and then column family name without any attribute to data type. So when at the time of the data insertion, put is the command of insertion. So put employee database and then you define the name. Name is attribute, the gender is attribute, and the city is attribute. So when you insert the data, you are storing attribute and name together. So the name of attribute is defined at the time of insertion and dynamically created. And then you can add the second data. So after adding this later, if you want to add another attribute for some employee, for example, let's say Hillary's next goal, priority is to become a president of the US. So now I want to create a new attribute for the priority, only to Hillary but not to Obama, because he's already president. So I can add just a new attribute for the priority using this put command here. So in this way, this will not create any null value problem to Obama here. It's physical. So null value problem is widely solved. So in this way, we can add as many attributes dynamically possible. So relational database is traditionally we use a conceptual modeling, logical modeling, and they create the physical table, and then we do the coding. But in NoSQL level, they do so-called the physical modeling first. They don't spend too much time on conceptual modeling, logical modeling. They just say what I need to write in my code, and then they write the code. But after like 1 week later, 1 month later, after one guy left and then they hired another guy, now they are in trouble. They don't know what are inside the code. So they need like a retrospective modeling. So they document what they have done in previous projects. So conceptual modeling or logical modeling is done after coding. So we need to change this practice. So in future NoSQL system, we expect you to do like some kind of logical modeling first. Paulo has a paper last year in ER conference on NoSQL design methodologies. That's a wonderful method, kind of a method that I want to promote in this community. So we try to have some abstract logical methodology that can be mapped into multiple NoSQL systems. So we need this like and monster type practice. So the first problem, the next problem in the impedance mismatch in the regular database we normalize data, all the atoms. And then is a table. But what we really is dealing with in real world is this kind of form, or some people call it aggregate. So all the data, related the data in one place. So we call them is an aggregate. So this aggregate is a unit of query and then unit of data consistency. So in NoSQL system, like a key store or document column store is kind of aggregating the database structure. Next is a no join. NoSQL does not have a join operation. So what does that mean? That means that we don't have a foreign key. And then if I need to make a join, it needs to be done in the code, in the program, not at the command level. So searching is usually done against a single table. And the single table, that's why single table needs to include a lot of data, all the relevant data, so that I don't have to look a second time. So in that way, when you create a database, we need to normalize the structure. So when you have one too many, many too many, you need to put that together. Of course, it depends on access tab. So you may need to redundantly create multiple tables. Even generalization, you need to put that together, all the hierarchy. So that creates the redundancy and the real interpret problem if it needs to be updated. So NoSQL is usually widely used in less frequently updated environment. So redundancy control means that in some NoSQL system, you can embed the data, or you can just reference data. It's not a foreign key, but it's just a raw key. So you still need a program-wide join. Foreign key means that at the command level, you can make a join. But reference means that you're joining into the application program level. So in embedding, you need to denormalize one-to-many, many-to-many relationships. So most NoSQL system also lack acid properties. So they are using so-called the eventual consistency. That means that if I update the data, eventually everything will become consistent. But some of my user may not be able to see my current most up-to-date data. That's why it increase the availability and the quick processing. So there are many variations of NoSQL. Even in single key value storage category, we have still many types. So in NoSQL, we have 4 types: key value, column store, document store, graph databases. And the key value means it based on Amazon Dynamo. It is simply a single hash table where your architecture looks like this. So you have a key, which is usually hash key, and everything related to the data are together as a block. That is kind of a binary format. So your program, if you want to understand what category included, what tag name included, you have to pass the data. So this is a powerful mechanism in the sense that you can quickly save it, quickly read it, and then you can distribute it before you need using distributed hashing techniques. So the goodness of a key value is a very fast random access and very scalable. This is why all in-memory grid systems are using this key value storage technique to distribute data across the network. So easy to distribute data across clusters, and the simple model as a hash table, and then Con is a more complex filtering query joining to the applications. And the column storage is quite interesting, and then it can handle a lot of different types of data structures. So the typical important thing you need to know is the typical key structure in column system consists of multiple, well, first of all, row key. This is not system-defined key, user-defined key. And then column family name, which is like a rescue table name. And the column qualifier, which is the column name. And then timestamp. So these are all 4 components that became primary key, or just a key. And then you value to retrieve. So data is accessed by this key, but by this order here. So order of key is very important. So if you need to analyze the time-based analysis, you need to move the timestamp to the early. You can define it by program. So timestamping supports the version control. And by default, the most recent value is retrieved automatically. And the rapid temporal analysis of the same row is possible. And the row key can be a composite key, but still stored as a single key. So this is an example of a single key here. So row key, this is a template. This is a multi-key template. So your row key has a multiple value, multiple attribute. So this is an example of a single key. And the example of a multiple key is stored like this. So we have a employee ID and the project ID are multiple keys. They are separated by a semicolon, but stored under the single row key. So you need to decide whether to use a single key, multi-key, where to put the timestamp. So how do we decide? You have to analyze the requirements. You need a logical modeling here. So column family, nested column family is a powerful technique in NoSQL here. So row key and the key attribute, and then single column is stored here. Column can be list, set, map, whatever structure. But this is the nested structure. So you can have a nested table that can be repeated as many times as possible. So some people use a column family. Some systems call it super column in Cassandra, for example. So columns are modeling aspects. It has a rich modeling structure. Some systems even support the secondary indexes. And so all the data access together in a denormalized form. So denormalization is common. But most importantly, you have to analyze the query requirements. So there are multiple ways to model for a given query requirements. So I found that logical modeling greatly helps. So for example, suppose I have a very simple ERD like this. So I have a posting. You post some website or blog here, and it has a set of tag many-to-many relationship. Every posting belongs to one category, so you have a one-to-many relationship. And then you add a lot of comments. You have multiple comments. And then there is a user who posts who make a comment. So if we model this in NoSQL, what it looks like. So for example, one-to-many relationship over here, one-to-many relationship between category and the posting here. So what happened? So what NoSQL schema options do we have? So in order to do that, we have to think about query requirements first. So obviously, if I have only these two relations, two tables, then two query requirements are for each category show me all the posting, display all the posting with the category names. So that's the two main. So we need two different tables for them. So for the requirements for each category show all the posting here, so we can design like this. So for each category, I will have a multiple nesting of a posting. So I designed the posting as a nested table. So I used the embedding in this case. Embed the posting into another category with a nested structure. And because it is a nested table, I used the column family. And then for each category show all the posting, on the other hand, I can use a referencing technique too. So instead of actually redundantly adding all the posting data, I can just use a posting ID in the form of inverted index style. So this is the inverted index design technique. But this is usually not a NoSQL style, because you need a join to the another table here at the program level, not at the command level. So, and the other query requirement, display postings with this category. In this case, this is the many side, so I can just redundantly repeat this. So I denormalize. So there will be a transitive dependency here. Category name, category description is just modeled as a column. So one-to-many relationship. If I want to have a posting per category here, so I can add the nested posting under the category name here. And if I have a posting with the category, then I have a title just using regular one. So we need to keep both tables in this case to satisfy both requirements. Because NoSQL's goal is a performance. So if I use only a single table, searching based on category name is almost impossible. It destroys the purpose of using NoSQL. So in order to just satisfy two query requirements, I need a two schema with the redundancy here. So posting is repeated in both sides. So inherit control is a big issue here. What about many-to-many? Even we have more trouble here. So posting and tag has a many-to-many here. Right? So requirements are, again, for each tag, show all the related posting. For example, I need to do health. I'd like to see all the posting regarding health. And to show the tags of each posting. I want to see which tag were used in which posting. So again, we can model in two ways here. So posting per tag. So for each tag, I can have repeated postings. And the posting with tag here. So I can just add the tag name in my posting. Again, I need a two one, only two here. But what if my many-to-many relationship has an attribute? My previous example did not have an attribute in the many-to-many relations. So what if I have a many-to-many relationship, like here? So message and the member like at a particular date. So we have a requirement like this. For each message, show who liked what message by like date and by message date. For each member, show what message he or she liked. And for each date, who liked what message, display message in the order of like date instead of message date or registration date. So these requirements need the different tables. So we can, just like earlier, we can create a table based on message, table based on member here. But also, we have another option. we can create a multiple table based on this light. So we have a composite, create a composite primary key. And each entity will model as a column family, the same. And also, if I want to search based on member ID, I need this. If I need to search based on message ID, I need this. So I need both of them. Once again, for the performance issue. So we are creating tremendous amount of redundancy in this pattern. So there is another option. What if we create another primary key for light? In other words, we ratify light relationship to an entity like this. So light ID here. So in this case also I can have a different structure. Okay. So this is a partial schema for the ERB here. It's already posting is in only partial schema. Posting is redundantly stored 1, 2, 3 times. So we are creating a lot of redundancy here. So the lesson learned here is for each access path we need to create an aggregated table which row key begins with the attribute used in searching. And for one-to-many relationship, we use a denormalized structure. For many-to-many, we have a lot of choices. You can use the aggregated technique, entity focus, relationship focus, one-way access, two-way access path, or even reversal timestamp map over here. And for generalization hierarchy, we can merge everything into a single superclass. So if aggregated times dependency, you may use a column family inside the aggregate. If sub-aggregate is a repeating group, use a nested structure. So some kind of heuristics. So you need to define whether they are valid. You need to do research. So the most important lesson I learned in multiple experiment is logical design is still important as useful. So we cannot just jump into physical design. So column storage is a diverse modeling structure, schema flexibility, and the form is a lot of table. Sometimes number of table in column storage is a lot more than relational table if you want to model everything together. This is why most people run against a single table or a few tables. So document store is much more powerful than column store, more genetic unstructured. So I once spent too much time on document store here. And the graph database, as I said earlier, this is not really NoSQL here. This is a express query and traversal using based on graph theory. And also it is not very partition friendly. So in that sense, it is not really NoSQL. It is just a non-relational database. So one of my students and I developed a system called a graph-based interactive bibliometric information retrieval system based on graph database. So let me quickly show you what we did and what are the results. So the contents here was just accepted by cases student. So we want to automatically generate the query based on form, and then also Cypher. Cypher is a query language used in Neo4j. So Neo4j is automatically created, and then the process of query and then return to the user. So that's a nice cycle. So this is the ERG. So we developed the ERG first to understand what objects are involved. And then we converted that into a graph schema, so-called a property graph schema. And then we created a database. Again, here you can see that it is a schema free. So initially we created a database. And the actual data is created at the time of the data load. And then age is created here, like N2 create relationship to N1. So from N2 to N1, I'm creating relationship for the writers. So we are creating dynamical data. So we use a graphic form-based interface. And then you enter the data here, it will be converted into graphic format. And the cycle query is generated. So later for the comparison, we load them into SQL and then compare it. So the relational schema is a little bit more complex than our original model. So we use about about 2 million data nodes and about 8 million total edge nodes. So we divided our query into 10 query for each kind of 2 node, 3 node, 4 node, 5 node to see what are the impact of the number of nodes to query performance. And we found that this red one is a graph database and the blue one is a MySQL. In 2 node query, the 2 node query, MySQL worked better. But in 3 query and then 3 node, 4 node, 5 node, consistently graph database worked best. So in terms of performance, there is no way to compare them. So blue is a graph database, red one is MySQL. So you can see that time spent in each query type is independent of number of nodes. This is the reason it does not do any join. It's just a traversal automatically. So just a fast number of nodes traversal is negligible. So important lesson learned is graph database outperforms relational database, and then number of query performance is independent of the number of nodes. And right now we are trying to compare with the in-memory database systems. So lesson learned from a modeling point of view, ERD is still useful in even designing graph databases. And then what's over, it helps to communicate. Graph database is so complicated. Think about visualization of 2 million nodes and then 8 million edges. It's impossible to explain to somebody. So in order to talk with the different people, we need some kind of ER diagram. But graph database does not support the n relations. Only binary relations to support, but domain friendly. So real world modeling concept can be directly created at the edge. And then it is also schematics. So pros, cons, etc. And then also for landscape. Since I'm out of my time here, let me go through several key points I want to show you. So what are the project management? I think a lot of people, according to survey, a lot of the data projects fail. And then, so we need to educate involve the people about data-driven culture and how to tie the technology with the business goal, and then developing analytics, and then big data technology here, solutions, and then concern about security and the leaders. So I'd like to bring your attention to so-called the data analytic lifecycle and the chief data officer discipline. So conventional data mining lifecycle is like this. Many of you have seen this, so-called the 6-step data mining model. But we want to divide that into 8 steps. The reason is that conceptual model, I don't want you to write a Java program or R program, right? That takes too much time. But we went to so-called a model planning. So here, model planning means for a given requirement, you identify what data mining machine learning technique you have to use, what measure you have to use to evaluate it. That's the model planning steps. And then you have evaluation. So this is where we can play a lot of roles. So you can hire people to build the model, actually to write the program. But this is the high level thinking and analysis you need. And then also evaluation stage. So here, step 4 and step 6, you can do a lot of work. So chief data officer means it is someone with a vision and strategies. You need to understand the global data policies, set out the governance quality. And then you need to ask the business question and the metrics and oversee the big data project. So chief data officer need a lot of skills, like leadership, communication skills, eye for business and the value, and the project management, and the big data analytics lifecycle, big data technology solution, and the data management skill and the system thinking. So this is a unicorn person. There is no one who can do all these. So you need to choose a few of them. You can excel others. But you can still try to develop your discipline. So I think big data problem solving is still computer science problem, largely, eventually, because we eventually end up with the analytic places. So what we can do here, in terms of research topic, I think the NoSQL design pattern is an excellent research topic. So you can customize NoSQL design pattern and develop some methodologies like Power, and then develop tools, and then tool-based commit and SQL visualization in graph database, standard query language, and then metadata management is a big issue here. So how you automatically detect the big data metadata and then visualize and then use it in our real-world process. So I recommend you participate in emerging technology like smart city, smart health, and then smart aging project or IoT. Or IBM is pushing new technology for the cognitive computing a lot. So IBM supercomputer Watson is based on cognitive computing. So my university is the IBM Watson school. So we are teaching Watson in our AI class. So we are experimenting with Watson here. So I've been involved with the aging research topic a lot here. So this is my domain analysis of my smart city, which I began my project 1 year ago. And then we reduced the scope with the smart aging technology using Watson here. And then we are in the middle of developing this smart analytic platform. And then we try to identify the Watson use cases. And then developing mobile app to Watson. And then how you incorporate the preference in healthy aging. And how to coordinate the training processes, support and evaluation here. I think there are a lot of things you can, conceptual modeling can do. And the notion of so-called digital colleague. Somebody who needs help, we don't always go to rely on the web here. And our university has one web sensor lab, which we can take advantage of it. So my conclusion is in big data world, conceptual modeling is still useful. You can do requirement analysis, project management, NoSQL database modeling, and then understanding big data concept and design architect, and the work on variety, etc. And then NoSQL are still early phase, but it will become more popular. And then, so you need to expand the scope, like to become a citizen data scientist, a CDO, and a data architect. And then most of all, some of you should identify new business opportunity, new data application disciplines. And also teach. I think we also teachers. We need to teach big data technology and big data analytics using automated tools rather than just R or Java. So, last year I wrote a paper called the Big Data and Data Science, what should we teach? So it was just accepted by Expert System Journal. I think you can access from the web if you have subscription to SLU. So predicting the future, the best way to predict the future is to invent it. So my last word is, you can do it better than this by Henry Kissinger, but that's his word. So what is my word? We can do better than this. Thank you.
Thank you, Il-Yeol, for this very comprehensive presentation and keynote talk. I think we should spend some 4 minutes for question and answering if there are some very urgent questions. Yes, please.
Hello. So thank you for a very interesting presentation, and it's really enlightening. You mentioned in the beginning that now it's a big concern what to do with data that is being collected in 20 years, 50 years, 100 years from now. And it seems that, okay, I understand big data is concerned with increasing performance, scalability, but consistency and consistency checks. How will we, I mean, for me, because for me it seems if we talk about 100 years from now, it's a problem of integration, because there will be different types of systems and you want systems to be able to have some reference framework to be able to understand the data that is collected today. But if you
always is for questions, please.
Okay, so if you're creating the database on the fly, how is consistency, or how is consistency going to be guaranteed?
So consistency in NoSQL-like system is maintained at the aggregate level. The data you store in a single table level. So everything within the single table will be consistent. But we cannot, sometimes we cannot guarantee not every system with a consistency between this table and another table. But later, if you want to create the data, then you need to maintain consistency.
Thank you. Other questions? Yes, please. Or we can ask a question between the microphones coming. The silence statements about all models are wrong. This is literally true. A model, in my opinion, is always true. It's only the process of generating it. If the model is technically very clear.
Okay, thank you. Thank you very much for your talk. I really enjoyed, especially from the point that you point out that adding value is highly relevant for us, for our community, and I completely agree with you, because one of the challenges I see at this moment is how we can predict the value that big data sources can add to our current analysis. However, I would like to know your opinion, because out of this community, when you submit a paper, when you talk to data scientists, they say, don't worry about conceptual modeling, because the more data we have, the smaller error we have with our statistical analysis. So if you don't pay attention to the value, you can predict in advance. So I would like to know your opinion on to know something else about discussions you have had with practitioners, with people that most of practitioners are for doing more statistical, more data mining analysis, and don't worry about the value in advance, because the more value you have, the more data, the more value we'll have. This is my first question or reflection. The second one is, I would like to know your opinion about the problem that we have to face up with getting data from external sources, because we are highly dependent on the application programming interfaces and the data structures data providers are giving us. You should have an architecture, and then they change the APIs, and it may change completely your architecture and your integration methodology. Do you have any opinion on how can we deal with all variations of programming interfaces? Thank you.
I think value and quality, I think in real world project, I think they are important. So when you write a paper, it may be different issue. In the research, it may be different issue, but when you work on real world project, value and quality are really concerned. Otherwise, you have spent a lot of time on some project, but if they don't get increased return on investment, they leave. So I think that's my first answer. I didn't quite understand your second question.
We are highly dependent on the structure and the application programming interfaces data providers are giving us. Twitter, Facebook, Google, APIs, and any data providers. If they change the data structure and the application programming interface we are working with, it may completely change your architectures.
Right.
So new data structures can come suddenly, so within the next 24 hours, and I would like to know your opinion about how dependent we are on those interfaces.
If you're using cloud or if you rely on other sources, you are dependent on that. So selection of cloud must be done very carefully. Once you are committed, you are bounded to the cloud vendor. So I think we don't have much control about that.
Now we have a coffee break, and then we can discuss all these things in much more details. Thank you very much again. We all want to say and naturally all the get here this wonderful data also. Thank you.